In this video, we'll talk about the uncertainty principle as it applies to qubits. As I had said in the last lecture, one of the advantages of working with qubits is that you can very precisely talk about rather advanced concepts, and you can see exactly how they apply. So let's go ahead and do that. So you remember in the last lecture we talked about this uncertainty principle of Heisenberg, where we had the electron going through one of two slits, and we said if you were trying to figure out which slit the electron went through, then you're going to inevitably, to try to measure that, you're going to disturb the system, and you'll disturb it if you could, to the extent that you figure out which slit, you're going to destroy the interference pattern. Okay, so here's the way that Heisenberg formulated his uncertainty principle. He said we can never know with perfect accuracy both of those two important factors which determine the movement of one of the smallest particles, its position and its velocity. So now, in what sense did that apply to the double slit experiment? You see that what we were trying to do was we were trying to pin down the position of the electron, whether it went through slit 1 or slit 2. And the point was, in our attempt to figure out which slit, we were giving it enough of a kick, so we were changing its velocity or its momentum sufficiently so that it destroyed the interference pattern. Okay, so now in this lecture we want to make all this precise in the context of a qubit, and we want to understand what this uncertainty principle really means. Later in the course we'll come back and we'll very briefly touch upon this uncertainty principle as Heisenberg posed it, but let's look at it in the context of a qubit. Okay, so let's look at two different bases for the qubit. So we have the 0, 1 basis. So this is an orthonormal basis for the two-dimensional complex vector space. And now we can define two other states. We can define a state which we call plus, which is just an equal superposition of 0 and 1. So it's this 45-degree oriented state vector. And we can we can define this vector. So remember, what does this mean? So remember, in the Ket notation, what this means is plus is just a name that we are giving to this vector. We could have called it psi, we could have called it x. We chose to call it plus. And I'll explain in a moment why. And then we define a corresponding state or a vector minus, which is 1 over square root 2, 0 minus 1 over square root 2, 1. You should check that they're both normalized, so they are unit vectors, and they're orthogonal to each other. The inner product is 0. Right? So the inner product is 1 over square root 2 times 1 over square root 2 plus 1 over square root 2 times minus 1 over square root 2. Okay, so these are orthogonal vectors as well. If you were to measure either of these states, plus or minus, you would see 0 and 1 with probability half each. So ground or excited with probability half. But what distinguishes these two vectors, the reason they're orthogonal is because of the sign or the phase in front of this excited state. And so this is why we refer to this as the plus vector and this as the minus vector. Okay, these are just names that we have given to these two vectors. Okay, so now let's say that if we were measuring in this basis, then we are determining the bit value of this qubit, because we are trying to figure out whether the qubit was in the state 0 or 1. So in other words, if we have some state psi which looks like this, we could measure it in this basis 0, 1, and we'd figure out what the bit value of this qubit is. And of course, this bit value might be, there was some chance that it would become 0, some chance it would become 1. Okay. After we measure it, we know for sure it's 0 or 1. Okay, but We can also be interested in figuring out a different quantity related to this qubit. We could measure it in the plus minus basis. And let's call that the sign value of the qubit. So in other words, if we were to measure this qubit psi in the plus minus basis, the outcome would be either plus or minus. And we'd have figured out the sign value of this qubit. Okay, so let me draw this analogy. Let's think of bit as corresponding to position and sign as corresponding to velocity or momentum. There's a certain sense in which they do. Okay? And so the question we'll ask is it possible to ever know with perfect accuracy both the position, both the bit as well as the sign of a qubit? So you're given a qubit in some unknown state, and you want to know both the bit value and the sign value. Okay, so what would a state look like where we know the bit value? Well, to know the bit value, to know it known perfectly, what must the state look like? Well, it must look either like 0 or 1. Of course, we can have an arbitrary phase in front, but let's ignore that for the moment. Let's imagine we are on the real plane, and then we don't want to worry about this unknown phase. What about for the sign value to be known perfectly? So for the sign value to be perfectly known, it must be in the state plus or minus. Okay, but can't we get close to knowing both perfectly? Well, here's the reason, here's what's keeping us from knowing them perfectly. The reason is that these make a 45-degree angle with each other. So now, if you have a state psi, as it tries to get closer and closer to either 0 or 1, it gets farther from plus and minus. So for it to be close to 0, it's got to make at least a 22.5-degree angle with both plus and minus. Same thing for 1. If it's close to 1, it's got to make at least a 22.5-degree angle with plus and minus. This gives us an uncertainty principle. You cannot perfectly know both the bit and the sign value. So what's the case for position and velocity or momentum? Exactly the same thing, except you're working in a much more complicated vector space. So working with qubits allows you to understand the principle in a much simpler setting. Okay, now for those of you who are really interested in understanding how one might make this this quantitative, this is, let me do one slide to tell you how to make this quantitative, but this is not really important. So if you're not, this is a good point to stop watching this video unless you're really interested in seeing this aspect of it. Okay, so what we can do is we can define a measure of how uncertain, how inaccurately we know the bit value and how inaccurately we know the sign value. So let's write out the state psi as in terms of as alpha 0 0 plus alpha 1 1, and we can also write it in the plus minus basis with amplitudes beta 0 and beta 1. And now we are going to define the spread in this standard basis, the 0 1 basis, as the absolute value of alpha 0 plus the absolute value of alpha 1, and in the sign basis it's absolute value of beta 0 plus absolute value of beta 1. So why did we define spread this way? So you see, when we know the bit value perfectly, the spread is 1, because we'll get either alpha 0 equal to 1 and alpha 1 equal to 0, or vice versa. In either case, the spread is 1. On the other hand, in the case that we don't know the bit value at all, the worst case is if we have the state plus, in which case we really don't know the bit value at all. Then the alpha 0 and alpha 1 are both 1 over square root 2. So the spread is square root 2. So the claim is that the only way the spread can be small, that it can be 1, is if you know the bit perfectly. And the farther from 1 it is, the more uncertain, the less certain you are about the bit value. The same thing holds for the spread in the plus minus basis. So plus and minus have spread 1, and anything else has larger spread. And in this time 0 and 1 have maximal spread of square root 2. And so what this uncertainty principle for bit and sign says is that if you look at the spread in the standard basis and multiply it by the spread in the sign basis of any qubit, then this product is at least square root 2. Which means that both of these values cannot simultaneously be 1. At least one of them, so either this must be at least square root of 2, so 4th root of 2, or this must be at least 4th root of 2. Okay, so that's the sense in which it's saying that you must be uncertain about either one or the other.